Greetings, everyone. I'm Professor Jeff Wilkerson, and this is an introduction to measuring the focal length of lenses in the General Physics Laboratory at Luther College. We're going to do work with this over 3 weeks, and this is an introduction to, the weeks won't necessarily be compartmentalized, so we'll do all of one thing one week, all of one thing the next week, and all of one thing the next week. But this will be mostly what we're going to tackle in the first week here in this particular video. And what we're doing is we're measuring the focal length of a lens, and two lenses. We're going to measure the focal length of two lenses. One of them claims to have a focal length of 10.0 centimeters, and the other claims to have a focal length of 20.0 centimeters. And we are going to see if we can make enough measurements with enough precision to be able to tell whether we can measure any deviation from those listed focal lengths. Are they what the manufacturer says they are? And what are they actually? So that's what we're trying to get in and look at. Remember, we talk about all of these things in terms of probabilities. So our goal is going to be to take enough data to maybe be able to make a histogram and fit a Gaussian to it and use the mean and standard error to understand how likely it is that the manufacturer's claimed focal length is consistent with what we see. To do this, we're going to use the thin lens equation. 1 over f is equal to 1 over s plus 1 over s prime. The situation looks like this. You've got a lens, you've got an object, and you've got the screen out here. We're going to use f is a positive number if we have a converging lens, and we're only going to use converging lenses in this experiment. And so those converging lenses will make real images on the screen out here so long as the object is outside the focal length of the lens. So we want to keep the object outside the focal length of the lens and map this space. We're going to just keep playing around with this and measure this as much as we can. We're going to get a whole bunch of solve this for f. We make an equation in Kaleidograph, for example, and we just have a column of s's and a column of s primes, and we go bam, 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 and measure a lot, and then do it again, and then do it again, and then do it again. And we can look for bias, we can look for inaccuracy that creeps in. Is the focal length, for example, is it consistent with s values? If you make a graph of your measured focal length as a function of your object distance, does that graph look the same in all regions of object distance, or does it show some sort of trend that suggests we've got some sort of bias in our measurements that's leading to some sort of inaccuracy, at least in a part of our measurements, that we need to maybe avoid that region? This is not at all unlike what we did measuring the index of refraction a few weeks ago. That first week, which is all we did, was try to determine what range of incidence angles was best for us to make that measurement. And you probably want to spend a little bit of time doing that kind of work here in the laboratory the first week as well. But you got two lenses, and so you're gonna want to go and get as much data as you can. You'll have time in the second week to take more of that. This is what it looks like. This is your setup. So you've got a light source on one end. I got to back out there so you can see it all. So your light source is down here, and here's your lens, and there's your screen. And you can move all of these relative to one another. So you've got s is the distance between the lens and the light source, and s prime is the distance between the light source and the screen. And you can slide each piece, each component can be moved around to make different s and s prime differences. And your task is to do so until you get a crisp image on the screen down here. That may be a challenge. You may not be able to tell exactly where the crispest image is, and you see where some uncertainty is creeping into your measurements right away because you don't know what the exact values of s and s prime are. And again, we will try to fix that issue, the uncertainty, the lack of precision that comes in from things like that. We will try to fix by taking lots and lots of data. Now, we may or may not be able to take lots and lots of data. We may or may not be able to fix it, that is, because there may be inaccuracy in there as well as imprecision. And so this is the things we've talked about quite a bit in this laboratory so far, and this is the kind of things we're going to keep working on. So anyway, you got two different, once you've made this measurement for one of these, you just swap in the other lens and make the measurement for the other lens. You got a couple of focal length measurements for two different lenses. One of them the manufacturer would claim is a 20 centimeter focal length, and one of them they claim is a 10 centimeter focal length. But we want to know what you get. What do you see when you make that measurement? So that's really what we're all about. This is your setup. This is what you're going to be playing with, and you're going to just use, much as you use Snell's law to determine the index of refraction, you're going to use the thin-lens equation in a very similar fashion to determine the focal length and go after it. So this is gonna feel experimentally in the laboratory. This first week is going to feel a lot like what you've been used to doing the last few weeks. So good luck with it, everybody, and I'm looking forward to it. It should be a fun measurement.